Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we discussed about the active earth pressure and passive earth pressure distribution, not passive earth pressure distribution, active earth pressure distribution when you consider the cohesion of the soil. And there we have seen that if you consider the cohesion of the soil, basically you will be getting some amount of tension at the top of the wall, right. So, and that tension will be extending from say z equal to 0 to z equal to z naught. So, up to that depth basically you will be getting some amount of tension on the wall, and beyond that. So, at z equal to z naught your pressure, active pressure will be becoming simply 0, and from that point onwards, that means z equal to z naught to z equal to h, basically you will be getting the compressive pressure whatever is generally you see for cohesionless soil, right. So, that is the main difference already we discussed, and based on that we got I mean few different parameters. One is the critical depth, right. So, that critical during that critical depth AC is nothing but 2 into z naught. Okay. So, that within that depth basically your negative pressure and your positive pressure means the compressive pressure. So, negative pressure means the tensile pressure. So, these two pressure will be getting nullified, and because of that you will be getting, or you generally get, and that you have seen in your practical, from your practical experience, that if you consider some cohesive C5 soil, basically you can excavate some amount of soil with some certain depth, right, without any support. So, that certain depth without any support you can excavate in cohesive soil, because that depth is less than HC, that is critical depth, that is 2 z naught, right. So, those things we saw in the last lecture, and we have seen another thing, that is soil does not stand any tension, right, and as such it is quite unlikely that the soil would adhere to the wall within the tension zone of depth z naught, producing cracks in the soil. So, and that is known as tension cracks. So, already we have seen in the last lecture that you will be getting tension cracks, and that is known as tension cracks, right. So, the area where the tension is coming, okay, within that depth, basically your soil cannot pull the wall, right. Soil is weak in tension. So, I mean you cannot expect some pulling effort from the soil, so that it can pull the wall back. So, that is not possible in soil, and therefore, what will happen, you will be getting some cracks because of tension. The soil will be experiencing some cracks in the tension zone, and that is known as tension cracks, as I wrote here. Okay. So, now based on that, okay, how can you modify the active earth pressure distribution plot in case of cohesive soil? So, this is the actual say active earth pressure distribution plot for cohesive soil, for C5 soil. So, this part is experiencing some tension. So, this is your negative pressure. Okay. So, this part, so z equal to z naught, within that zone you will be getting tension, and from at z equal to z naught you will be getting say 0 pressure, okay, and then from that point onward you will be getting compressive stress, right. So, ultimately what is happening here, so this negative pressure and this positive pressure, they are symmetrical. So, this much, I mean up to z equal to z naught, whatever negative pressure you will be getting, that will be simply equal to the compressive pressure or the compressive stress, okay, that is coming within this zone, right, and they are cancelling each other, right, and that is why you are not getting any pressure, virtually you are not getting any pressure on the wall. But frankly speaking, so when we are going to design okay, the wall, we do not consider this nullifying effect or this cancellation effect, okay, in the active earth pressure distribution. What we consider, so instead of this kind of, say, this is the shaded part which is actually acting on the wall, which is compressive in nature, and this is nothing but the active thrust, active pressure on the wall, right. But we do not consider like this kind of diagram, rather we consider the diagram like this, where your compressive pressure. So, we are simply neglecting the tensile pressure, and we are not thinking, or we are not telling that the tension is going to cancel the positive, some amount of positive pressure. So, that thing we are neglecting, and we are considering that the total compressive pressure or total compressive thrust, active thrust, is acting on the wall starting from z equal to z naught. So, this is the point at z equal to z naught, and it is going to end at point z equal to h, okay. And this is the, if you see the previous expression, previous equation for Pa, that is the active earth pressure distribution, active earth pressure. So, at z equal to h, okay. So, this is the active pressure gamma h by n phi minus 2 c by root over n phi, where 1 by n phi is nothing but Ka, right, already we have seen that. So, this is the, now basically this is the total pressure distribution we will be considering when we are going to design some wall, some retaining wall, okay, under the active pressure in cohesive soil, in C phi soil, okay. So, we are not considering, we are not cancelling any part of, so this part we are not cancelling, or we are not ignoring, rather we are considering the total triangular distribution of the active earth pressure. Now, based on that we define, or we calculate the total active thrust Pa, okay. Now, this depth, okay, along which you have actually the pressure on the wall. So, that depth is nothing but h minus z naught, because z to z naught you have the tensile pressure, or the tensile, I mean pulling or tensile nature of active pressure, okay. So, that we are neglecting. So, therefore, at z equal to z naught, at z equal to 0 to z naught we do not have any pressure. So, all of a sudden the pressure is getting started from z equal to z naught to z equal to h. So, the total depth along which the pressure is acting, that is nothing but h minus z naught. So, that means that the wall, if you think physically, the wall up to depth of z equal to z naught is not experiencing any kind of pressure, okay, because we are neglecting the tension or the tensile pressure, and tension is not, I mean it is not possible for soil to carry the tension, right, and that is why you are getting the tension cracks. So, the top portion of the wall from z equal to 0 to z equal to z naught, that portion of the wall will not be experiencing any pressure from the active thrust, rather the pressure will be starting from z equal to z naught, and it will extend up to z equal to h, and that you are getting from this diagram, right. So, it is very unlikely, I mean if you compare with your cohesionless soil, in the cohesionless soil the top part or the top portion of the wall was experiencing 0 pressure, and it is gradually increasing with the linear distribution. But in this situation, up to a certain depth it is, there is no pressure, and then from z equal to z naught your pressure is getting increased on the wall, right. So, you can design the wall in such a way that, I mean the top portion is not experiencing any pressure. So, therefore, total pressure active, I mean the total pressure or the active thrust, so whatever, that is a force, that is Pa, right. So, this Pa is nothing but, if you see this, so this is at z equal to z naught, okay. From there we are getting this pressure, okay, that is gamma h by n phi minus 2 c root over n phi, right, and this depth is h minus z naught. So, we have just seen in the previous slide, right. So, total thrust will be nothing but the area under this triangular plot, this is your total thrust Pa, okay. So, that Pa is nothing but the area of this triangle. So, that means half into gamma h by n phi minus 2 c by root over n pi into h minus z naught. So, this is the total thrust, and why it is acting? It is acting h minus z naught by 3 distance above the base. So, this is nothing but this. Okay. So, this is the point of application of this active thrust P A is nothing but h minus z naught by 3. Okay. So, I hope that you have understood the basic difference between the cohesionless soil and the cohesive soil. Okay. So, in the cohesive soil the pressure the active earth pressure can be calculated by this expression, whereas in case of cohesionless soil you calculated active earth pressure P A is equal to half into what, half into K A into gamma into H square, right. So, this is the thing. I mean, here in this equation if you put C equal to 0, suppose you want to find out the active earth pressure for cohesionless soil. So, that means C equal to 0. So, if you put C equal to 0, Z naught will be 0, okay, and C will be 0. So, this part will be going, this part will be going, and this part is nothing but half into gamma H into K into H. So, you are getting the same expression whatever we have got earlier, right, if C is 0, fine. So, I hope that you have understood this concept. Now, based on this concept we are going to calculate the Rankine passive pressure for cohesive soil. Okay. So, we have seen how to find out active thrust, active pressure for the cohesive soil, that is C5 soil, that means if C is there then what will be the expression for active pressure. Now, we are going to find out the expression for passive pressure if C is there. So, basically your sigma 1, and that is the relation already we know from our earlier discussion, that sigma 1 equal to sigma 3 n phi plus 2 c root over n phi, right. Now, in case of passive pressure already we have seen that in case of passive pressure what is sigma 1? Sigma 1 is nothing but the lateral pressure, that is the horizontal pressure, that is sigma h, which is nothing but P p, that is the passive pressure, am I right. So, in case of active sigma 1 was the vertical pressure, in case of passive the horizontal pressure will be your major principal stress. Similarly, sigma 3 in case of passive pressure what will be the sigma 3? Sigma 3 is nothing but the vertical pressure, that is nothing but sigma v, which is equal to gamma z. So, if I put these things in this expression, okay, so I will get an expression like this. So, P p is equal to gamma z into n phi plus 2 c root over n phi, where n phi already we know n phi is nothing but 1 by k, which is nothing but 1 plus sin phi minus 1 minus sin phi, which is nothing but k p, right. So, gamma z n phi is nothing but gamma z k p plus 2 c root over n phi, instead of that I can write 2 c root over k p. So, this is the pressure, this is the passive pressure along the wall depth of h. Okay. So, now what we are going to find out at z equal to 0, that means at top of the wall what is the passive pressure, what is the, is it 0? So, it was 0 for cohesionless soil, earlier we have seen that if z is 0 then immediately you are getting 0 passive pressure in case of cohesionless soil. Now, whether that will be same for cohesive soil, is it so or not? So, we are going to see that. Okay. So, at z equal to 0, so P p from this, from the previous expression given in the previous slide. So, P p is nothing but 2 c into root over n phi, okay, is equal to 2 c into root over k p. Okay. So, this is the passive pressure we are getting at z equal to 0. That means, instead of becoming 0 passive pressure, 0 pressure at the top of the wall, you are getting some amount of pressure which is positive, which is compressive, that is okay. Okay, that is not like active pressure where you are getting some tension. Here you are not getting any tension, but you are getting some amount of pressure, positive pressure at the top of the wall. So, your top of the wall is not free from any pressure, it has got or it has experienced some amount of pressure. So, at z equal to h, what is the value of P p? That is the passive pressure. P p is equal to gamma h into n phi plus 2 c into root over n phi. So, in the previous equation, if you put z equal to h, you will be getting this. So, now if I plot this, so I will be getting this plot. So, this is the wall of depth say h. Okay. This is the failure surface, linear failure surface. Now, I am getting this part. So, this is nothing but 2c into root over n phi, which is nothing but 2c root over k p. So, this is the pressure at top of the wall. So, it is not stress free. Okay. At top of the wall you are getting some amount of pressure, and from that point basically you are getting the linear distribution, and the total the pressure at the base of the wall you are getting gamma h n phi plus 2c root over n phi. So, this part is gamma, this part is 2c root over n phi, and this part is gamma h n phi. So, this is the total pressure at passive pressure distribution. So, the passive pressure distribution curve will look like this. Okay. So, now the total thrust, total passive thrust, if you want to calculate, what you can do? You can get the area of this whole trapezoid. So, this is looking like a trapezoid, right. So, you can find out, or you can determine the area of the trapezoid, and that area of the trapezoid will give you the total passive thrust. Now, for sake of convenience, we are not going to determine the total area of the trapezoid, rather we are distributing, or we are dividing the total area of this trapezoid in two parts. In one part we are getting this rectangle shown by this dash line, okay, and another part we are getting some triangular distribution. So, in the rectangular distribution, the total thrust, the area of the rectangular distribution is say PP2 if it is PP2, and this is your say PP1, okay. This is a PP1. So, the total thrust on the triangular part will be say PP1. So, that means the area of the triangular zone will be PP1 and the area of the rectangular zone is say PP2. Now, we can calculate this PP1 and PP2, and we can find out the point of application of these two forces separately. Okay. So, PP2 is acting at h by 2 from the base, right. This is your h by 2, and PP1 will be acting h by 3, yes or no, right. So, we can calculate each individual forces thrust as well as the point of application of each individual forces, and if I want to find out the resultant force as well as the resultant force point of application, then we can take the moment with respect to point A and we can find out that, okay, as before we have done. So, PP1, okay. So, PP1 is equal to half gamma h square into n phi, right. If you look at this figure, so this is gamma h n phi and total depth is h. So, half gamma h square into n phi. So, that is your PP1, that is nothing but half gamma h square into Kp, which will be acting at h by 3 from the base, as I told you, okay. Whereas, PP2, that is the area of the rectangular portion, that is nothing but 2 C h into root over n phi, that is nothing but 2 C h into root over Kp, right. So, that is the area of the rectangular portion, and that will be acting, as I told you, at h by 2 distance from the base. So, from this PP1 and PP2 you can find out the total passive thrust, that is total passive thrust is nothing but PP1 plus PP2, okay. And the point of application of PP, if you want to find out, you have to take the moment equilibrium with respect to point A for these forces, okay. So, I hope that it is clear. So, that means now you are well equipped to find out the active pressure in completely cohesionless soil as well as passive pressure in cohesionless soil. Now, also you can find out the active and passive pressure in cohesive soil as well. okay, and you know that what will be the difference if you deal with some cohesive soil, okay, and if you deal with some cohesionless soil. Okay. Now, if you have the backfill with sloping surface, so it is very common, right. So, all the times you will be getting the backfill which is horizontal, it may not happen in the real life, right. So, if you want to retain the hilly slope, okay, so suppose the hilly slope is like that, and if you want to retain that thing with your retaining wall, okay. So, this slope, so if you have this kind of inclined backfill, then what will happen, okay, let us see that. So, if you have the inclined backfill, that means, so this is the wall, okay, which is having the inclined backfill, which is inclined at an angle beta, okay. Now, we are considering one soil element, so E like this, which will be experiencing some inclined lateral pressure sigma L and vertical pressure sigma V. Therefore, if you take out this soil element, so this is the soil element, say, so this is your sigma L which is acting parallel to the sloping surface, sloping backfill, okay. So, that is nothing but your lateral pressure, okay. So, inclined lateral pressure. Now, sigma V is the vertical pressure, okay, and B, where B is the, say, this inclined length, okay, B is the inclined length, say. So, therefore, the horizontal length will be B cos beta, okay, because the angle of inclination is beta, okay. Now, we can calculate sigma n and tau. What is sigma n? Sigma n is the normal stress on this sloping surface and tau is the shear stress along this sloping surface, okay. So, now, for this I can calculate sigma V. What is sigma V? Sigma V is nothing but the vertical stress. So, that is nothing but gamma z into B cos beta, right. So, that is the total force, yes or no, that is the total force gamma z into B cos beta divided by B will be your vertical stress gamma z cos beta, right. Similarly, sigma L, that is the lateral pressure, that is nothing but PA, that is our objective to obtain, to find out, okay. So, sigma L is this PA. Now, we are going to find out sigma n and tau. So, sigma n is nothing but sigma V into cos beta, the component of sigma V along the normal direction. So, sigma V cos beta is nothing but sigma n, which is nothing but gamma z into cos square beta, because sigma V itself is equal to gamma z cos beta. Similarly, tau is equal to sigma V sin beta, okay. So, now if you look at this figure, basically you will be getting all those things. So, tau is equal to sigma V sin beta. So, sigma V is nothing but gamma z cos beta into sin beta. So, you are getting tau equal to gamma z sin beta cos beta. So, at any depth, okay, you can find out sigma n by this expression if you know the slope of the backfill, the depth which you want, and of course, if you know the unit weight of the soil, you can find out sigma n, that is the normal stress at any depth. Similarly, you can find out the shear stress at any depth, that is nothing but gamma z sin beta cos beta, okay. So, once you know this, okay, so if you know sigma n and tau, that is the normal stress and the shear stress. So, point A2 is fixed in tau sigma space, we are now plotting this point, okay. In tau sigma space, the point A2 is fixed if we know, so this is the point, okay. That point is fixed in tau sigma space if I know sigma n and tau, so because A2, the coordinate of A2 is sigma n and tau, okay. So, that is shown here, okay. So, once point A2 is fixed and if I join point A2 with the origin O, that will make an angle beta with the horizontal, with the sigma axis, agreed. It has to be, yes or no, it has to be, because the inclination already you consider that inclination is beta, inclination of the sloping surface or the sloping backfill, right. So, based on that you calculated sigma n and tau, right. So, the point, this point is now fixed if you know sigma n and tau. Now, if you join this point with the origin point, origin O, then it will make an angle beta with the sigma axis, with the horizontal, right. Okay. Now, draw a Mohr circle through A2 and tangential at M. So, now you are drawing one Mohr circle through point A2 and tangential at point M. Now, what is point M? Point M is lying on the Mohr Coulomb failure envelope, because this angle is phi and you are considering completely cohesionless soil. So, this will be your Mohr Coulomb failure envelope. Okay. So, this is the Mohr circle which is passing through point A2 and which is touching at point M, which is telling you the failure, right. When the Mohr circle is touching at point M, so point M is telling you about the failure. Okay. Now CM, so this is the point C, C is the center of the Mohr circle, M is the point, okay, at the at the Mohr circle, but it is touching with the failure Mohr Coulomb failure envelope. So, that is point M. So, if you join these two points C and M, basically it will give you the radius, right, it will give you the radius of the Mohr circle. So, radius of the Mohr circle is nothing but OC into sin phi. What is OC? OC is the distance between origin O and center of the Mohr circle. So, several times we have seen this thing when we are discussing about the Mohr circle and the shear strength and all those things, several times we have seen that. So, Cm is equal to OC sin phi. Now, what is Cm? Cm is the radius of the Mohr circle. Now, how can I express that? Sigma 1 minus sigma 3 by 2, agreed, okay, is equal to what is OC? OC is the distance between the Mohr circle center and the origin. So, that can be expressed as sigma 1 plus sigma 3 by 2 into sin phi. Okay. Now, therefore, I can write sigma 1 minus sigma 3 is equal to sigma 1 plus sigma 3 into sin phi. Okay. So, got it. Now, we are trying to find out few points or the few references. So, now what is OB? OB is nothing but this, the point, this is the line and this is the point B. Now, what is B point? B is the point if you draw a normal, okay, from point C to the line OA2, okay. So, you will get the point B. What is B? B is the point if you draw a normal from C on the line OA2, you will be getting point B. Okay. So, OB is nothing but OC into cos beta, agreed, very simple from the geometry, from the figure itself. Okay. So, what is OC? OC we have got sigma 1 plus sigma 3 by 2. So, therefore, I get sigma 1 plus sigma 3 by 2 into cos beta. Similarly, I am going to find out BC. Okay. So, BC is equal to OC sin beta. Okay. So, again that will be equal to sigma 1 plus sigma 3 by 2 into sin beta. Okay. Now, A1B, what is point A1? A1 is the point on the Mohr circle where OA2 line is cutting the Mohr circle or intersecting the Mohr circle. So, A1. So, I am getting 2 points A1 and A2 already we have established, based on that we have drawn the Mohr circle. So, A1B is equal to A2B from the geometry or from the property of your triangle and the circle. Okay. So, A1B must be equal to A2B is equal to what? A1 root over A1 C square minus BC square. Okay. So, from this what is A1C? A1c is nothing but the radius of the Mohr circle, which is nothing but equal to cm. So, that I am getting here, okay. And BC, what is BC? BC just now we have calculated sigma 1 plus sigma 3 by 2 into sin beta. So, that we are putting here, okay. Now, what is this sigma 1 minus sigma 3 by 2? That is nothing but sigma 1 plus sigma 3 by 2 sin phi, okay. So, A1b is equal to A2b, therefore, sigma is equal to sigma 1 plus sigma 3 by 2 into root over sin square phi minus sin square beta. Now, what is sigma v? If you look at this figure, sigma v is nothing but OB plus BA2, because this is your sigma n, because the A2, the coordinate of A2 is sigma n and tau, that is normal stress and shear stress. So, sigma v is not the normal stress, please try to understand, sigma v is not the normal stress, and sigma L is not also the normal stress, right. So, if you want to find out sigma v is nothing but the component of sigma n in the vertical direction, okay. So, that is nothing but OB from the graphical representation, OB plus BA2. So, OB plus BA2 will give you sigma v, yes or no? Yes, right. So, that is nothing but we can get sigma 1 plus sigma 3 by 2 into cos beta plus sigma 1, that is nothing but BA2, already we have got it here, okay. That we have got, sigma v we have got. Now, sigma v is not the matter of concern for us. We are going to find out the sigma L, that is the lateral pressure, yes. So, sigma L is nothing but the active earth pressure, that is what, OB minus A1b, because you can understand sigma v is acting vertically and sigma L is acting parallel to the sloping surface, right. So, sigma L will be OA1 basically, sigma A will be OA1. So, how will get OA1? OB minus A1b. So, OB already you have got it, okay, from the previous calculation, and this is your A1b, which is nothing but A2b, okay. So, this is your lateral pressure. So, sigma L you have got, sigma V you have got. So, your Ka will be sigma L minus sigma V. You have got lateral pressure, you have got vertical pressure, the ratio of these two will be your Ka. So, in the next slide we are going to see that. So, Ka is nothing but sigma L by sigma V, and which is nothing but Pa is the sigma L, that is the active earth pressure, divided by, already we have calculated, do you remember, already we have calculated sigma V, which is equal to gamma z cos beta, right. Now, this is the thing we have got earlier. Now, this is now sigma L and sigma V, just now we have got the expression for that from the Mohr circle. So, that if I put here, so I will be getting one expression, big expression like this, Pa is equal to cos beta into this part into gamma z. So, that we can write as Ka into gamma z. So, therefore, this whole part is your Ka. Now, you put beta equal to 0 here, you will be getting simply 1 minus sin phi by 1 plus sin phi. Okay. So, when beta is there, right, at that time your active earth pressure coefficient will be taking the form like this. So, you have to calculate the active earth pressure coefficient from this expression, and then it will be remaining same. So, Pa will be equal to Ka into gamma z, that Ka automatically will take care of the inclination effect from this expression. Okay. So, similarly, I am not going in much detail for the passive thrust. In a similar fashion, you can find out the passive earth pressure coefficient in the sloping backfill. Okay. So, that will be equal to cos beta into this part. So, that will give you the passive earth pressure coefficient for inclined black field. Okay. So, now you can see the how the pressure distribution is working. So, this is the inclined backfill. So, BC is your inclined backfill, which is inclined at an angle beta. So, AB is the wall. Okay. So, now the triangular distribution is this, it is 0 at the top and at z equal to h, this is the pressure, okay, inclined pressure. So, inclined total thrust is Pa, which is inclined at an angle beta with the horizontal, and the point of application is h by 3. Please remember, Pa is acting with an inclination of beta with the horizontal. Okay. So, now basically so far what we have seen, whatever active earth pressure coefficient or passive earth pressure coefficient we have calculated. So, those are based on Rankine's analysis. So, Rankine did not consider the friction of the wall. That means, he considered wall is very smooth and there is no friction in between wall and soil, right. So, that means, say suppose if this is my backfill, okay, and if this is my wall. So, if I want to separate it out, so this is the wall, say. So, I do not have any interface friction, okay, at the backfill and wall interface. So, that smooth condition or the frictionless condition was considered by Rankine. Now, it is not always true. Suppose you are using concrete wall, which is more common in real life, right. So, I mean smooth wall, generally you will be seeing that if you use stainless steel wall or something like that, which will be having smooth surface. So, there is no friction, I mean you can consider there is no friction at the interface. But if you use a rubble masonry wall or brick wall or even concrete wall, you will be getting enormous amount of, or I mean significant amount of friction at the interface, right. So, that friction must be taken care when you are calculating the active and passive earth pressure coefficient, and that was proposed by Coulomb. So, we will see now that Coulomb's method for calculating active and passive earth pressure coefficient, which will consider the wall soil interface friction. Okay. Now, we will go to the board and we will see that how we can write down, or we will give the complete say expression for active and passive earth pressure coefficient by Coulomb. So, as I told you that Coulomb's mechanism, that Coulomb generally consider the wall soil interface friction. So, so far you have seen in the Rankine's method that you do not consider the interface friction. That means, you consider the wall is completely frictionless, that is smooth wall, right. But Coulomb's proposed. So, Coulomb's active and passive earth pressure, we are going to see that. Okay. So, how we will be getting different expression for active and passive earth pressure coefficient. So, now what is the basic difference between Coulomb and Rankine? So, Rankine earth pressure calculations are based on the assumptions that the wall is frictionless This is the basic difference between Rankine and Coulomb's mechanism. Okay. Rankine did not consider any friction at the interface of the wall and soil. So, Rankine earth pressure calculations are based on the assumption that the wall is completely frictionless, okay, but which is not the case in the real life. You will be getting some interface friction. That means, if soil, so when in case of active case the soil wedge is coming down, it will try to come down, right, along with the wall, and you will be getting some resistance at the wall soil interface. So, suppose if this is the wall, this is the backfill. So, if I say this is the backfill, in case of active situation, it will try to move in the downward direction, am I right. So, you will be getting some resistance in the upward direction, right, and this resistance is basically based on the interface friction. Okay. So, if soil wall interface friction is not there, then this kind of resistance will not be developed. Okay. So, in case of passive, so this block is will try to move in the upward direction. So, you will be getting the resistance in this direction, right. So, this resistance is very significant, and this resistance will be there. If you consider the friction, interface friction, if it is there, then of course, this resistance will be developed, and to calculate this resistance you need to know that how much interface friction is there. So, whatever may be the case, if interface friction is there, so there you cannot use Rankine earth pressure theory. So, whatever you have seen K value or Kp value, whatever you have calculated so far for cohesionless soil or for cohesive soil, those things will not be valid if you consider wall is not frictionless. Okay. If wall is frictionless, it is okay. If wall is not frictionless, you have to use Coulomb's earth pressure theory. Okay. So, Coulomb's theory takes care of the friction, soil wall interface friction. Okay. That is the basic difference between Coulomb's and Rankine's theory. Okay. Now, in case of active case, let me draw it. So, I am showing the figure for most general situation, okay, where you have the wall inclination that is defined by say beta, you have the inclined backfill that is defined by alpha, okay, and this is your say failure wedge, okay, in the backfill side, and which will be experiencing some, because this is the active state. So, this block, this wedge will try to move in the downward direction. So, you will be getting the development of the shear resistance S, okay, along this surface in the upward direction, and this is the normal force and this is the resultant force R. So, this will be developed based on the shear resistance mobilized at the failure surface, okay, fine. So, theta 1 is the angle of inclination of the failure surface with the horizon. Okay. So, now you need to calculate or need to find out Pa. So, I am not going in much detail that how you will find out all those things. So, this is based on the limit equilibrium method. If you consider the force equilibrium as well as the moment equilibrium of the system, then you can find out the magnitude of Pa. So, I will be giving you the direct expression for Pa rather going for the detailed calculation of Pa. Okay. So, and this W is the weight of the wedge. So, if you consider all the forces and if you consider the force equilibrium as well as the moment equilibrium, then you can find out the value Pa. Okay. So, Pa will be given by, so Coulomb's active force is given by Pa, that is the active thrust. Pa is equal to half into Ka into gamma h square. This expression is similar, only thing is that the difference will be happening in the expression of Ka. So, instead of 1 minus sin phi by 1 plus sin phi, you will be getting something else, or maybe if you are considering the inclination of the wall, whatever you considered earlier. In case of Rankine, already we have derived that, right, from the Morse cycle. I hope that you remember. So, that will not be valid for this Coulomb's analysis. Okay. So, this Ka value will be the Coulomb's active earth pressure coefficient. So, Ka is your Coulomb's active earth pressure coefficient and is given by sin square beta plus phi divided by sin square beta into sin beta minus delta into 1 plus root over sin phi plus delta sin phi minus alpha by sin beta minus delta sin alpha plus beta whole square. Okay. Now, everything is defined. What is beta? Beta is the wall inclination, wall face, that is the back face of the wall inclination. Alpha is the inclination of the backfill soil, backfill slope. Okay. And delta, what is delta? Delta is nothing but the angle of interface friction. So, delta could be 2/3 of phi, 1/3 of phi. Generally, it has been seen that it is 2/3 of phi, right. So, delta, if it is soil interface, then of course, it will be phi. So, as it is the wall and soil interface, so delta will be less than phi, or maximum it can go up to phi. So, delta could be 0 and it could be maximum, it could be phi. So, if delta becomes 0, you will see this expression will be same whatever expression you have got just now from the Rankine's analysis. Okay. But if delta is not 0, that means if the interface friction is there, that means the soil wall interface friction is not 0, then in that situation the active earth pressure coefficient must be calculated from the Coulomb's analysis, and that will take the form like this. Okay. So, I can write down this in the actual design of retaining walls. The value of delta is assumed to be between phi by 2 and 2/3 of phi. Okay. Now, in case of passive case, what will happen? So, in case of passive case, what will happen? So, let me draw it. Okay. In case of passive case, this S will be going in the downward direction, because the whole block will be trying to be lifted in the upward direction, right. So, N is the normal force and R is the resultant force, which will be acting at an angle phi with the normal force. Okay. So, that these forces will be developed along this failure surface. So, these details I am not talking about, this is kind of little bit more advanced details. Okay. So, any book, if you want to find out how to find out all these forces, you can refer any book on the advanced topic. Okay. W is the weight of the backfill wedge or the failure wedge. Okay. So, beta is the angle of inclination of the back face of the wall, alpha is the again same, that is the angle of inclination of the sloping surface. Now, PP is the active thrust. Now, which will be making an angle delta, because delta is the angle of internal friction, right. So, which will be making an angle delta with the normal to the back face. Now, you see, because wall, I mean the wedge, failure wedge will be trying to be lifted up, will be moving in the upward direction. So, PP will be acting in this direction, whereas PA was acting in this direction. So, if you look at this, okay. So, this is the basic difference between the direction of PA and PP. So, if in this situation, so Coulomb's passive force, PP therefore is equal to half Kp into gamma h square, where Kp is nothing but Coulomb's passive earth pressure coefficient, and that is given by sin beta minus phi divided by sin square beta sin beta plus delta into 1 minus sin root over sin phi plus delta sin phi plus alpha divided by sin beta plus delta sin beta plus alpha whole square. Okay. So, this is the expression. Now, you put delta equal to 0, you will be getting the same expression whatever we have got for passive case from the Rankine's analysis. Okay. So, anyway, so this is all about your earth pressure theory on the retaining structure. So, I hope that you have enjoyed this part, this topic, because this is very important. So, I am not going to the design part of the retaining wall, because they are actually, by using this earth pressure coefficient, you can calculate the pressures, and based on that you can find out the stability of the retaining wall. Stability means external stability as well as internal stability. So, external stability, there are several external stability, sliding or overturning or bearing capacity, all those things. So, those things are purely on the design aspect of the retaining wall, so which are beyond the scope of this course. So, I'll restrict myself at this point, where we have come across the earth pressure, okay, developed by the soil on the retaining wall. So, this much is sufficient to know, okay, to understand the earth pressure concept. Okay. So, I will stop here today. So, in the next class we will talk about the stress distribution. That means, if you have any kind of foundation or any kind of say structure, okay, beyond that part, what will be the distribution or how much stress will be coming. So, that will be seeing next, and then of course, the numerical problems will be solved for earth pressure as well as stress distribution together at the end. So, thank you very much.